Welcome to the fascinating world of quantum mechanics. In this video, we'll embark on a journey to understand one of the most fundamental equations in physics, the Schrodinger Wave Equation. Quantum mechanics describes the behavior of particles at the smallest scales, where the rules of classical physics no longer apply. This field has revolutionized our understanding of the universe, from the structure of atoms to the behavior of light and matter. Before we dive into the details of the Schrodinger Wave Equation, let's set the stage by exploring why quantum mechanics is so important and how it differs from the physics we experience in our everyday lives. Early 20th century was a time of great discovery in physics. Scientists like Max Planck and Albert Einstein began to realize that energy is quantized, meaning it comes in discrete packets rather than being continuous. This idea was revolutionary and laid the groundwork for quantum theory. Classical physics couldn't explain phenomena like blackbody radiation or the photoelectric effect, but quantum theory could. These discoveries set the stage for Erwin Schrodinger to develop his famous wave equation, which would become a cornerstone of quantum mechanics. Erwin Schrodinger was an Austrian physicist whose work changed the course of science. In 1926, he introduced the Schrodinger wave equation, providing a mathematical framework to describe how quantum systems evolve over time. Schrödinger's equation allowed scientists to predict the behavior of particles like electrons in atoms, something that was impossible with classical physics. His contributions earned him the Nobel Prize in Physics and cemented his legacy as one of the founding fathers of quantum mechanics. Wave equation is a mathematical description of how waves, such as sound or light, propagate through space and time. In classical physics, wave equations describe things like water waves or vibrations on a string. Schrödinger's insight was to apply the concept of waves to particles. He proposed that particles like electrons could be described by wave functions, which encode the probability of finding a particle in a particular location. This was a radical departure from the idea of particles as tiny, solid objects. Wave function, usually denoted by the Greek letter psi, is a central concept in quantum mechanics. It's a mathematical function that contains all the information about a quantum system. The square of the wave function's magnitude gives the probability of finding a particle at a specific point in space. This probabilistic interpretation was a major shift from classical physics, where the position and momentum of an object could be known exactly. In quantum mechanics, uncertainty is built into the very fabric of reality. Schrödinger wave equation is the mathematical heart of quantum mechanics. It describes how the wave function of a quantum system changes over time. In its most common form, the equation relates the energy of a system to the way its wave function evolves. This allows physicists to predict the behavior of particles in different situations, such as electrons in atoms or molecules. The equation is both elegant and powerful, providing deep insights into the quantum world. There are two main forms of the Schrödinger equation, time-dependent and time-independent. The time-dependent equation describes how a quantum system evolves over time, while the time-independent version is used for systems with constant energy, like electrons in a stable atom. Both forms are essential for understanding different aspects of quantum mechanics. The time-independent equation is especially important for solving problems like the energy levels of atoms and molecules. Let's take a closer look at the mathematical form of the Schrödinger equation. In one dimension, the time-independent equation is written as h2/2m d2 psi/dx2 plus vx psi equals psi. Here, psi is the wave function, h stroke is the reduced Planck constant, m is the mass of the particle, v, x is the potential energy, and E is the total energy. This equation allows us to calculate the allowed energy levels and the shape of the wave function for a given system. Schrödinger equation isn't just a mathematical curiosity, it has deep physical meaning. It tells us how quantum systems behave and evolve. The solutions to the equation, called wave functions, describe the possible states of a system. By analyzing these solutions, physicists can predict the outcomes of experiments and understand the structure of atoms, molecules, and solids. The equation bridges the gap between abstract mathematics and the real, observable world. One of the most surprising aspects of quantum mechanics is its reliance on probability. The Schrödinger equation doesn't tell us exactly where a particle is, but rather the probability of finding it in a certain place. This probabilistic nature is a fundamental feature of the quantum world. It means that at the smallest scales, nature is inherently unpredictable. This idea challenged the deterministic worldview of classical physics and led to many philosophical debates. See the Schrödinger equation in action. Let's consider a classic example, the potential well. Imagine a particle trapped in a box with infinitely high walls. The equation predicts that the particle can only have certain discrete energy levels. These quantized energy levels are a direct result of the wave-like nature of particles. This simple model helps us understand more complex systems, like electrons in atoms or quantum dots in technology. Another fascinating prediction of the Schrödinger equation is quantum tunneling. In classical physics, a particle can't pass through a barrier if it doesn't have enough energy. But in quantum mechanics, there's a non-zero probability that a particle can tunnel through a barrier even if it seems impossible. This phenomenon is crucial in many technologies like tunnel diodes and even nuclear fusion in stars. Schrödinger equation can be solved exactly for the hydrogen atom, the simplest atom in the universe. The solutions reveal the allowed energy levels and the shapes of the electrons' orbitals. These results match experimental observations perfectly and provide the foundation for our understanding of atomic structure. The success of the equation in explaining the hydrogen atom was a major triumph for quantum mechanics. Solving the Schrödinger equation for atoms introduces the concept of quantum numbers. These numbers describe properties like energy, angular momentum, and orientation of electron orbitals. Quantum numbers help us understand the arrangement of electrons in atoms and the periodic table structure. The shapes of orbitals predicted by the equation explain chemical bonding and the behavior of elements. Schrodinger equation allows for the principle of superposition, meaning a quantum system can exist in multiple states at once. This leads to phenomena like interference and entanglement, which have no counterpart in classical physics. Superposition is at the heart of quantum computing and many other emerging technologies. When we measure a quantum system, the wave function collapses to a single outcome. Before measurement, the system exists in a superposition of possibilities. This collapse is one of the most mysterious aspects of quantum mechanics and has led to famous thought experiments like Schrödinger's cat. The measurement problem remains an open question in the foundations of physics. Schrödinger equation is closely related to Heisenberg's uncertainty principle, which states that we can't know both the position and momentum of a particle exactly at the same time. This fundamental limit is built into the mathematics of quantum mechanics and has profound implications for our understanding of reality. Schrödinger equation embodies the concept of wave-particle duality, where particles like electrons exhibit both wave-like and particle-like behavior. This duality is a hallmark of quantum mechanics and is observed in experiments like the double-slit experiment. The equation provides a mathematical framework for understanding this strange but fundamental aspect of nature. Schrödinger equation is essential in chemistry, where it explains the structure and behavior of molecules. By solving the equation for different atoms and molecules, chemists can predict chemical reactions, bonding, and the properties of materials. Quantum chemistry has led to the development of new drugs, materials, and technologies. Modern technology relies heavily on quantum mechanics and the Schrödinger equation. Semiconductors, lasers, and magnetic resonance imaging (MRI) are just a few examples of technologies that wouldn't exist without quantum theory. The equation's predictions have been tested and confirmed in countless experiments, making it one of the most successful theories in science. Quantum computing is an exciting new field that harnesses the principles of quantum mechanics, including the Schrödinger equation. Quantum computers use qubits, which can exist in superpositions of states, to perform calculations far beyond the reach of classical computers. The Schrödinger equation helps describe how qubits evolve and interact, paving the way for breakthroughs in computation and cryptography. Entanglement is a phenomenon where two or more particles become linked, so the state of one instantly affects the state of the other, no matter the distance. The Schrödinger equation predicts and describes entanglement, which has been confirmed in experiments. Entanglement is the basis for quantum teleportation and secure communication. Quantum cryptography uses the principles of quantum mechanics to create secure communication channels. The Schrödinger equation helps describe how information can be encoded and transmitted using quantum states. Quantum key distribution, for example, relies on the unpredictability and measurement rules of quantum systems to ensure security. Quantum teleportation is a process where the state of a particle is transferred to another particle at a distance, using entanglement and the principles described by the Schrödinger equation. While it doesn't involve moving matter instantly, it allows for the transfer of quantum information, which could revolutionize communication and computing. Quantum dots are tiny semiconductor particles whose properties are governed by the Schrödinger equation. By controlling their size and shape, scientists can tune their electronic and optical properties. Quantum dots are used in displays, solar cells, and medical imaging, showcasing the practical impact of quantum mechanics. Quantum sensors use the principles of quantum mechanics to achieve unprecedented sensitivity and accuracy. The Schrödinger equation helps describe how these sensors work, enabling applications in navigation, medical diagnostics, and environmental monitoring. Quantum sensors are pushing the boundaries of what we can measure and detect. Recent research suggests that quantum mechanics and by extension the Schrödinger equation may play a role in biological processes. Examples include photosynthesis, enzyme activity, and even bird navigation. Quantum biology is an emerging field that could transform our understanding of life at the molecular level. Schrödinger equation has led to many interpretations of quantum mechanics, each trying to explain what the mathematics really means. The Copenhagen interpretation, many worlds, and pilot wave theories are just a few examples. These interpretations address questions about measurement, reality, and the nature of the quantum world. One of the biggest puzzles in quantum mechanics is the measurement problem. The Schrödinger equation predicts a superposition of states, but when we measure, we see only one outcome. How and why this collapse happens is still debated. This problem touches on the nature of reality and the limits of scientific knowledge. Schrödinger's cat is a famous thought experiment that illustrates the strangeness of quantum mechanics. A cat is placed in a box with a quantum device that can kill it depending on the state of a particle. According to the Schrödinger equation, until we look, the cat is both alive and dead, a superposition of states. This paradox highlights the challenges of interpreting quantum theory. Decoherence is the process by which quantum systems lose their quantum behavior and start to behave classically. The Schrödinger equation helps describe how interactions with the environment cause this transition. Decoherence explains why we don't see superpositions in everyday life and is a key concept in quantum computing. Quantum field theory extends the ideas of the Schrödinger equation to fields, rather than just particles. This framework is essential for understanding particle physics and the fundamental forces of nature. Quantum field theory unifies quantum mechanics with special relativity and has led to the discovery of new particles and interactions. The original Schrodinger equation doesn't account for the effects of special relativity. To describe fast-moving particles, physicists developed relativistic versions like the Dirac equation. These equations combine quantum mechanics with relativity and predict phenomena like antimatter. While the Schrodinger equation is incredibly powerful, it has its limitations. It doesn't include relativity or describe gravity. For these, we need more advanced theories like quantum field theory and attempts at quantum gravity. Understanding these limitations helps guide future research in physics. Physicists are searching for a theory of quantum gravity that unites quantum mechanics with general relativity. The Schrodinger equation is a key stepping stone, but a complete theory remains elusive. Research in this area could unlock new insights into black holes, the early universe, and the fundamental nature of space and time. The predictions of the Schrodinger equation have been confirmed in countless experiments. From the spectra of atoms to the behavior of electrons in solids, the equation's accuracy is unmatched. These experimental successes have solidified its place as a cornerstone of modern physics. The Schrodinger equation is a central topic in physics education. Students learn to solve the equation for different systems, gaining insight into the quantum world. Understanding the equation opens the door to advanced studies in physics, chemistry, and engineering. Visualizing wave functions helps make quantum mechanics more intuitive. Graphs and animations show how the probability distribution of a particle changes over time. These visual tools are essential for teaching and research, making abstract concepts more accessible. Quantum simulations use computers to solve the Schrodinger equation for complex systems. These simulations help scientists study materials, chemical reactions, and even biological processes that are too difficult to analyze experimentally. Quantum simulations are a powerful tool for discovery. The future of quantum mechanics is bright, with new discoveries and technologies on the horizon. The Schrodinger equation will continue to play a central role as scientists explore quantum computing, communication, and new materials. The quest to understand the quantum world is far from over. Quantum mechanics and the Schrodinger equation in particular have profound philosophical implications. Questions about reality, determinism, and the nature of observation challenge our deepest assumptions. Philosophers and physicists continue to debate what quantum theory really tells us about the universe. Mysteries of quantum mechanics have captured the imagination of writers, filmmakers, and artists. The Schrodinger equation and related concepts appear in movies, books, and television, inspiring new generations to explore science. Quantum mechanics has become a symbol of the unknown and the possibilities of the future. Despite its successes, quantum mechanics presents many challenges. Solving the Schrodinger equation for complex systems is often difficult or impossible analytically, requiring advanced computational methods. Researchers are constantly developing new techniques to push the boundaries of what we can predict and understand. Erwin Schrödinger's contributions have left a lasting legacy in science. His wave equation is a pillar of modern physics, influencing everything from chemistry to technology. Schrödinger's work continues to inspire scientists and students around the world, shaping the future of research and discovery. In summary, the Schrödinger wave equation is much more than a mathematical formula. It's a gateway to the quantum world. Its predictions have transformed science, technology, and our understanding of reality. As we continue to explore the mysteries of the quantum realm, the Schrödinger equation will remain at the heart of discovery, guiding us toward new horizons in physics and beyond.